We talked about PEG and just PE and PE elastic. We've got one more to talk about, and that's PE electric, potential energy electric.
Well, at least we don't have to do any math.
Yeah, you don't. You don't.
You just have to know it exists.
You just have to know that it exists. So now you have electric potential energy. So this is equal to the inverse of the charge times the field strength, which remember we're not going to calculate, times the displacement from that point in the direction of the field. Huh? Yeah, exactly. What do you need to know? Potential energy is directly related to the magnitude of the charge and how strong the field is and how far away you are from it. So, the bigger the charge, the more potential energy. The closer you are to the point charge, the stronger, the more potential energy. The stronger the electric field, the more potential energy. Okay, that's all you need to know, and that's more than enough for most of you. It's too much for some of you.
Potential energy is directly related to the distance.
The charge, the field strength, and the distance. Yeah, and you can see that just looking at this equation. You look at this equation and mathematically, because you guys are all solid mathematically, you know that if this goes up, this goes up. If this goes up, this goes up. If this goes up, this goes up. Whee! So that's pretty darn easy. Okay. When we did the circuits unit leading up to Physics Olympics. So potential difference. So we have established that there is electrical potential energy, but calculating it is all about individual charges, which means every single time the charge changes or the field changes, the potential changes. So the amount of potential energy can fluctuate wildly. We can have electrical potential energy that's just doing this from second to second. That's pretty useless for us, for our purposes. So what we tend to talk about is the potential difference. So this is, let's go back to the waterfall example. Do you remember the waterfall example from potential difference? So when we talk about potential difference, we go back to that waterfall example. If we think about potential energy due to gravity at this waterfall, let's say that we have 100 joules of energy here, and here at the bottom, how many do we have? 0. It's hit 0. Okay. Well, what if this, let's say this is elevation above the earth. Okay. And this is, we're going to make all this really simple, 100 feet, and this is sea level. Well, what if this waterfall exists in some weird magical corner of the planet where the entire bed of the river just keeps shifting? So you go out today and it's at 100 feet and sea level. You go out tomorrow and it's at 90 and 10 below sea level. You go out the next day and it's at 150 and 50 above sea level. That's bizarre. What has not changed in any of those scenarios? The potential energy. Because the difference in potential energy is still the same. The elevations are changing wildly, but the amount of the gap between the top of the falls and the bottom of the falls is the same every single day you go out. So there's always 100 joules of energy that water has at the top of the fall before it goes to the bottom of the fall. That's why we deal with potential difference, not potential energy electric. That's the analogy. Does that make sense? Okay. So we're not concerned with what the absolute value of the charges are. We're just concerned with how much difference there is. Okay? Okay. So V, do you recognize V? What does V stand for in electronics? Voltage. Finally, something that makes some sense. Voltage. Rather than Q again. So your change in voltage is equal to the change in potential energy electric divided by the charges that we're dealing with. You don't need to know that, but you'll have seen it at least.
Sure that's
Okay,
real.
we're going to talk about capacitance. This is a chapter 18 concept. We've skipped a lot of stuff that was the more involved math having to do with potential difference. So I hope you'll forgive me for that. What if you want to store a charge? What if you want to store some amount of charge to release it at a later date to run something? So you create some amount of potential difference between 2 points, and you want to store that charge. Capacitors are a very simple way to store a charge. And what you do is you have the most common form is a parallel plate capacitor. So within a circuit, and these are schematic symbols, if you might remember them from the brief unit we did on circuits before. And you have, basically, you line up charges. So you end up with, for instance here, electrons stripped off one plate and all waiting over here on this plate. And you have to have some material in here that is insulative. Okay? Otherwise, they would just cross the gap immediately. Air is an insulator. And so very often, the simplest capacitor is just called a parallel plate capacitor. It's 2 plates separated by an air gap. How many of you have ever used a computer keyboard? You have used a capacitor. When you press the key on the keyboard, what you are doing, somewhere down in there in the guts, is a small parallel plate type capacitor. You are closing the gap and discharging the stored charge. And that tells the system, type a Q, type a V, type an E. Yeah, with all kinds of complicated binary stuff. So that's a parallel plate capacitor. We can go in. We're not going to go into measures of capacitance, but capacitance is basically the amount of charge that you can store. It's the net charge on each ratio of net charge on each plate to the potential difference created by the separated charges. Because of course this creates a difference in electrical potential. And all this stuff wants to flow to there. Because you've now got a difference. Everything is trying to get down to a level. Water wants to fall over a waterfall. Electrons want to float where there are no electrons. Simple enough. Do you remember current from our brief unit on circuits? What is current? In a nutshell. Movement of charge. You have charge moving. So you either have electrons moving, thump, 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 like little ants on the march. Well, that's actually, they are the charge carriers, so yeah, they're the only thing that can move. Not all charge is electrons. You can have positive or negative charge, which is a loss or a gain. But anyway, charge carriers are electrons. Electrons are the only things that flow. You can't get protons to flow. Current is the rate of charge flow. So if we use the river analogy, the current is how much water is passing a given point at any given time. So if we look at a cross-sectional area of our river, so this is, I'm looking on at the river and I sliced it down and I've put up a plexiglass wall and I can see the water and the rocks in the bottom. If I measure, a 1 inch section in this surface area, how much water moves past that point every second? And in a river system, we typically talk about that in cubic feet per second, CFS. In electronics, we talk about, of course, amps, amperage. So current is the charge passing through any area over a unit of time. And current is given, it's an I, and that's delta Q over delta T. So that's the change in charge, how much charge travels past the point per second, really. Again, recall from the unit on circuits, the unit for current is the amp, and 1 amp equals 1 coulomb moving past a point in 1 second. Okay, so let's look at page 695, 19A. Okay, so number 1 on 695, 5 milliamps of current. How long does it take for 2 coulombs of charge to pass a point in the wire? We rearrange to solve for time, for seconds, and that gives us 2.00 coulombs divided by 5.00 times 10 to the negative third amps. So we get 400 seconds. 400 seconds.
10 to the negative plus 3.
Okay, 400 seconds, and we would have to put it into scientific notation to get the correct sig fig. So 4 times 10 to the second seconds. Okay, fairly easy, like stupidly easy. Number 4 on 695 is part of your homework.
Yeah.
Okay, so in direct current, this is DC, charge carriers move. This is the kind of current you get from a battery. Okay? Batteries can only provide direct current. What's the other kind of current? Alternating. AC. You're familiar with AC, DC? There used to be, and I don't think there are anymore, appliances that you could run on AC or DC. They were variable. They had a switch. In alternating currents, based on what we just did out in the hall, I think you'll remember for the rest of your lives. In DC, the charge carriers move. In AC, they stay in place, but they basically vibrate back and forth. They cycle back and forth. Yeah, they give you a headache. With AC, we measure that frequency of that vibration, that reversal of current, and that's your frequency. So in the U.S., it is 60 hertz. It is not 60 hertz every place. If you go to Europe, household standard, you have to get plug adapters because household standard is a different frequency. So yes, you will blow up your devices. You can only get DC out of a battery. So if you have a little battery, there's our little battery, that is DC only. There is no way to make a battery provide AC. Can't do it. You can build a generator. And when I say generator, I don't just mean a gas-powered generator that sits out in the garage that you use when the power goes out. I mean a power plant is a generator as well. You can construct a generator that will do either DC or AC. Now, how many of you have ever been in any sort of motorhome, trailer, okay, a truck with appliances? Actually, a lot of vehicles have these now too. Can you take something out of your house and plug it in to a car battery? No, because the appliance that you use in your home operates on what? AC. The car battery provides what? DC. How do you fix that? With a transformer. There are, and actually they're called inverters. They're called inverters. Yeah, and the inverter converts the direct current into alternating current. If you build a house that is off-the-grid solar, I knew some people in southern Ohio who had this situation. So they had the battery shed. Okay, we'll talk about it tomorrow.